Hello students, welcome to the fourth lecture on D and A flock element. In this lecture we are going to discuss the oxidation state of the transition metal element, that is D block element. So heading of this today's lecture is oxidation state, and that is physical property transition of element, that is the part 3. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. All the transition metal elements, when we study, what we find that except the first member and the last member of each series have the variable oxidation state that has been shown by those transition element in their compound. Now, what are those transition elements? That is, what are those oxidation state? Let us first understand. So, oxidation state, that is, it is being displayed by the three transition element that we are observed. That is from +1 to, that is ranging from the +7. So, that is in the transition element, that is first element that we know, that is the scandium, and it is having the electronic configuration is 3d1 4s2. Then we know it is a titanium. Titanium is having the 3d2 4s2. 3d9 4, that will be 3d10 and 4s1, and J that will observe, that is 3d10 4s2. The oxidation state that is shown by this scandium, that is +3. Only oxidation state it will observe. In case of titanium, it will be +2, +3 and +4. In case of vanadium, it will be +2, +3, +4 and +5. For chromium, it is +2, +3, +4, +5 and +6. The manganese, that is +2, +3, +4, +5, +6 and +7. In iron, it is observed, that is +2, +3, +4 and it is +6. The cobalt we observe +2, +3 and +4. In nickel we also observe +2, +3 and +4. Copper we observe +1 and +2, and zinc is for +2. This all the oxidation state you can observe. That magnesium, it is having manganese, it is having the maximum number of oxidation state, that is you can see 6 oxidation state. Scandium, that is 1, titanium 3, and vanadium, that is you can see 4, manganese, chromium, that is 6, and manganese, that is 6, manganese 6, chromium 5, and you can see as we go along the series that this number of oxidation state has been at the middle of the series, that you will find the maximum number of oxidation state shown by this element, that is manganese. Whereas in the, as we go further, what we find that the other, that is iron having only 4 oxygen state, then cobalt is 3, neon is 3, and copper 2 and 1. So this has oxygen state, and in that oxygen state, maximum oxygen state shown by this, that is also driven by a very important factor up to this plus, up to this middle of the series. It not applicable here also, latter part of the series. On the middle of the series you will find there is a rule. Rule is this: maximum oxidation state shown by this is equal to the D plus S electron. That sum of the D electron and the S electron, that will be given by the maximum oxidation state given by this element. As for example, titanium, that you don't understand, that is 4 electrons is available, D plus S. So here you will find maximum oxidation state is 4. In vanadium you can see 5, the maximum oxidation state is 5. Chromium, it is 6. Manganese is 7, it is 7. But afterwards you will not find this change. And here also we can see there is all the oxidation state are not the common oxidation state. There are some oxidation state that we will find for this element, it is common. As for example, for the titanium, plus 4 is very common and it is very stable. And here in the vanadium you will find that is plus 5 and plus 2, it is stable. In the chromium you will find that is plus 3 and plus 6. Magnesium, it is plus 2 and plus 6. Ferrous you will find plus 2 and plus 3. Cobalt you will find plus 2 and plus 3. Nickel you will find plus 2. Copper you will find plus 2. And zinc you will find plus 2. So if we compare all these series element, that is the oxygen state of the series element, what we find? We find one very basic thing, that is the most common oxygen state among these elements is plus 2, except the scandium, this was the plus 3, that you can see here is plus 2, plus 2, plus 2, plus 2, plus 2, plus 2. So it is plus 2 oxidation state is very common among the transition element. And maximum oxidation state, that is given by this formula D plus S, D electron and S electrons. And that is for your information. I would say, if we see all the transition elements, what we find, that is the maximum oxidation state observed is plus 8. And this is for osmium and ruthenium. In the osmium, that you will find, that is in this compound OSO4. In this compound you will find this. So we understand there is a variable state of oxidation state in the transition vector element. We have observed this in case of 3D transition series. Okay, now one thing that is we want to understand, why these transition elements show such kind of variable oxidation state, that we want to understand. Why it is so? That is due to this reason that N-1 D orbital and NS orbital, these two orbitals having the very little energy gap, and due to this factor, as there is a very little energy gap, the electron of both the orbitals can be used in the bonding, and that is why they show such type of variations. And it is also that due to this incomplete fielded of the d orbitals. D orbital is in this transition element is incompletely fielded, And so that what we observe, that the transition metal element, oxidation state of the transition metal element, we will found there is a gap between the two of its oxidation number by 1 unit. That you can see for the vanadium, that you have +2, +3, +4, +5. There is a gap of only 1 unit. This type of things is not observed in case of p block element, where you can observe in the p block element, where you can observe the variable oxidation state, different oxidation state, that is vary by 2 units. As for example, nitrogen +2, +3, +5. So there is a gap, difference between the two oxidation state, consecutive oxidation state, that is 2. Here it is 1. Okay, so we understand what is the reason behind this type of high oxidation state, that we understand that is basically due to the very less energy gap between n-1 d electron and ns electrons. Okay, so what we understand now, that we will see this in different compounds, that is in the halides and the oxides. Basically, that is a maximum oxidation state, that is for the magnesium, that is the manganese. Maximum oxidation state, Mn, we can observe, that is in case of fluoride or oxide. Because of this fact, these two elements, that is the fluoride and oxide, is basically a very electronegative. Due to this high electronegative element of oxygen and fluorine, what we found in their compound, it will show the maximum oxidation state. So now we understand with the reference of different compounds how the oxidation state has been manifested in this compound by those elements. 3 plus 1. For titanium, this is the oxidation state. For titanium, we know that you will observe the maximum oxidation state, that is TiX4. Titanium, that is tetrahalide, TiX3 and TiX2. In this case, in the TiX2, what we find is X is equal to, you can write, that is fluorine to iodine. Whereas in X2, there is this, for this case, we will find that is the chlorine to bromine. Then for vanadium, that is, it will observe that is 5 maximum oxidation state, you can observe that is the +5, and it is in case of fluoride. After that, you will find this tetrahalide of vanadium. In this case, you will observe this halide is excluding the iodide. Fluorine to bromine. Then trihalide, and then you will observe this dihalide. In the dihalide also you will find that is, it is do not have the fluorides, just like the dihalide in case of titanium. The chromium also you can see the maximum oxidation state, that is CrF6, then CrF5, then CrX4, chromium, okay. And for manganese, what we find that oxidation state, that is for simple halide, it will not show highest oxidation number. For simple halide, it will be start from this, that is a +4 oxidation number from the fluoride, tetrafluoride of magnesium, then trifluoride of the magnesium, and then MnX2. Okay. But this can be shown in this compound, that is MnO3F. In this compound, you can see this +7 oxidation state. Normal simple halide do not show this. After that, what we find, that is from the iron, that is it will have this ferrous tetrahalide, ferrous trihalide, and another compound we found ferrous. And in this case, you will find that here also there is no iodide is produced. Here the halide is, that is the fluorine, that is in the fluorine to bromine, no iodide. Okay. Now for the cobalt, you will find the cobalt also COF3 and COX2. For the nickel, we will find last oxidation state. The copper, we will find this. For this, you will have that X2 is basically the X of XR. Here, the dihalide you will find that is only fluoride and chloride is observed. And CuX, that is in this case, that is basically here these three. So both the cases you will find the halide is different, and in the gene it is. So what we observe, that is try to understand it, that is the maximum oxidation state that is observed in case of fluoride. You can see for the vanadium also, in the chromium also, maximum oxidation state you can observe. Why it is so? Because the bond enthalpy is very high in case of fluoride, but in the fluoride do not support the lower oxidation state. In case of titanium dihalide or vanadium dihalide, or you can also, that is in case of this copper X, copper halide, all the cases you cannot find the fluorides. Okay. Now we can see another thing, that for this tetrahalide of vanadium or here trihalides of the ferrous, you will find iron, you will find there is no iodide is produced. And in case of copper dihalide, you can find only the fluorides and chlorides. So what we observe, that is a variety of tint, and you have to remember the exceptions only. This exception, that in case of titanium this exception is there, for the vanadium this exception is there, and this also is there. So we have to always remember that. Question will ask in this fashion, that we have been given the product and we have to certify whether this product will be produced, whether it's okay or not, that we have to give. So in this case we understand the different type of oxidation state as being given by these compounds, by these elements in their compounds. Now we are going to discuss, this is the stable halide, now we are going to discuss the oxide. H2O3. Here you can see scandium is only one oxidation number, that is the +3, and you can see the group number, it is just matching. In case of titanium, that you can observe, that is TiO2, then oxide, Ti. So you can see here also maximum oxidation number is +4, that is correspond to this group number. Here chromium also we can see, the chromium, the maximum oxidation state is observed, that is a CrO3. Maximum oxidation state observed in, sorry, this is first we have to, vanadium is there, the first one is the vanadium B2O5, that is the maximum oxidation state is +5 and it is group number is +5. Here you can see this compound is produced, and where you can see it is so the oxidation +4, this is B2O3 and BO. In case of now the chromium CrO3, here two oxidation state 5, that is the 5 number will not be produced, but this will. Okay. Now that you can see maximum oxidation state is corresponding to the group number. Now in the, that is that is the manganese. Manganese you can see Mn2O7. Whereas in case of fluoride we will not able to see this +7 oxidation state. In the simple halide we can found only in the oxy compound that we will observe. Here in the oxides of this element that we will find this oxidation number. Then it is now for iron. Iron, it is a group number 8. Now that is for cobalt you can find, that is this is group number 9, this is group number 8, and group number 10, that is where you need to understand, that is nickel oxide, and group number 11 that we find, that is copper oxide and Cu2O, and last that is the zinc. So what we observe in case of oxide, that it will show the maximum oxidation state in the manganese, whereas in the fluoride it is not able to show. So from this we can able to understand one very important fact, that is oxide is much more strong in producing or in revealing the oxidation number, and that is why it is so. That is due to this fact that oxygen can able to form the multiple bonds, double bonds it can able to form. That is why it will able to show this maximum oxidation state. Now we going to understand the trend of the oxidation state in the down the groove. In the p-box element, due to this inert pair effect that you will observe, that the higher oxidation state is not being stable for the higher members. Higher members always prefer the lower oxidation state. But in case of d-block element, what we observe as we go down the groove, the higher members, the oxidation state will be much stable for the higher oxidation state. As for example, that is in the group number 6 is chromium. Chromium, that is his higher oxidation state in the dichromate CrO4 2-, it has oxidation state plus 6, but it acts as an oxidizing agent. But in case of molybdenum or tungsten, the oxide, where also you saw it is also observed this plus 6 oxidation state, but it is much more stable. So higher compounds, higher members of this group will always have the higher oxidation state, which is very much stable. Another thing that we have observed, that oxidation number, that is variable oxidation. The complex compound, that is NiCO4 2, or complex compound, that is CO2. For this compound, it will show the oxidation number of nickel is 0. Oxidation number of nickel, it is 0. Oxidation number is 0. And here oxidation number of ferrous iron, that is also 0. And here you can see this is called the carbon monoxide, as this is called CO, this is called the ligand. Ligand basically makes the accept the electrons from this metal by pi bonding, and that is why it will show the 0 oxidation state. So we understand the oxidation state of the transition metal element, and you will observe that it is going to show a variable oxidation state, and majority of the elements except the first member, the last member of this group, and we understand why it's so, and why first number and last number group do not show the variable oxidation state. Let us first understand why it is so. Because for the scandium or titanium, you can observe there is a very less number of electrons to lose or share, so they will going to have the lesser oxidation state. And in the last, that is copper and zinc, what we will find? We will find there is a more number of d electrons, and so there is a very less electron vacant orbitals, d orbitals is available, less vacant d orbital, so there is no place for sharing these orbitals, so they will show the lesser valency. So that is why they show the lesser oxidation number. Now question arises, how this oxidation state among these all the oxidation state, how this is going to be stabilized? How do we assure that? For that, we have to understand the electrode potential. That we will discuss in the next lectures. Thank you very much for watching.